All right, in this video, I'm going to introduce cylindrical coordinates, which are basically the equivalent of polar coordinates or a mixture of polar and rectangular. So the cylindrical coordinates of a point P in space is a combination of polar and rectangular coordinates. A point P in space is going to have three coordinates, r, theta, and z. And we can interpret what those mean that give us the location of P by projecting P down onto the xy plane. So let me project P onto the xy plane, and its image, let's suppose, is over here on the xy plane. I always call an image with it, let's say a P prime. This image, its coordinates are r, theta, 0, since when we've projected this, z now is equal to 0. Okay, now, on the xy plane, we can locate P by its distance from the origin, which we're going to call r, just like we do with polar coordinates, and the angle that the point makes with the x-axis. And so this is going to be our theta. And so you can see here that z is actually just the height from the image up to the point P, right? So that will be the z value of our point P. And here is, oops, that's a little bit crooked. Let me try that again. There we go. Here is x, and here is y. So you can see that the relationships that held before between polar coordinates and rectangular coordinates continue to hold. So the important relationships that we have then are going to be, the identities that we have is, one, if you look at the xy plane, we can see that x squared plus y squared equals r squared. We can also see that tangent of theta is y over x. And we define x to be r times the cosine of theta, just like with polar coordinates. Y is r times the sine of theta. And z is just z. Z doesn't change. So these are our cylindrical coordinates, and our conversion factors are the same as before, these two as well as these two. Now, let's think about why this might be useful. So let's consider changing the following surface, equation of a surface, to cylindrical coordinates. So convert the surface z equals x squared plus y squared to cylindrical coordinates. And the reason this is helpful is because using cylindrical coordinates can help us express equations that might be pretty messy in a very clean way, very easy to integrate or to use as limits of integration. And so, of course, we know here that x squared plus y squared is r squared. That is a relationship that we have for the polar coordinates, and we can use that to replace z, or x squared plus y squared, in z, and write this as z equals r squared. And that's our equation. These are equivalent equations that represent the same paraboloid, right? So this is a paraboloid. As r increases, so does z. So we get something that looks like this, our paraboloid. Okay, let's also think about what does the equation, let's say r equals 2, so let's describe this equation to figure out what this is in space. Describe this object in space. So if we think about this, well, r is 2. That means in cylindrical coordinates that both theta and z will vary, but r does not. And so if r doesn't vary and stays at 2, then let's take a look at our xyz coordinate system and see what happens when r stays put, but we let theta and z vary. So thinking on the xy plane, when r is 2, well, we know we have a circle of radius 2. So we've got a circle of radius 2 on the xy plane. And if z varies, well, we know that's going to give us a cylinder. And if theta varies, same, right? That's going to give us all of the points along the circle. As we move, we can draw some traces of our cylinder as we move up along z or down along z. And we see that this is just going to be a cylinder whose projection onto the xy plane is a circle of radius 2. And so describing this cylinder with cylindrical coordinates is actually very, very nice because we can just say r is equal to 2.